Hello, we are Team 1063 in the Simio Challenge using Differential Equations Modeling 2023 competition. My name is Alec Fialkov, and my partners are Maximillian Roach and Philip Williams. We will be presenting our solution to Problem B, Punishing Infants. We would like to thank our coach, Mr. Reece, for his support.
We were tasked with developing a mathematical model of a society in which people have a propensity to act out against those who interact aggressively towards others and examine how the populations within the society change over time. We were asked to determine the effects of various societal characteristics, including differing behaviors and opinions regarding the appropriate level of punishment within the population. We identified the factors impacting the stability of a society and what methods will result in more beneficial outcomes. Lastly, we were to discuss what societal changes on the attitude towards punishment would be beneficial based on the results of our model. Before we could begin modeling, we had to define certain terms. Our model has three populations. First are transgressors. These are people who act aggressively towards others against the terms of society, which we define as against the law. These people have a chance to become bystanders when they are punished for their transgression. Next are punishers, who are the people with a desire to punish transgressors when they act out. Punishers have a chance to burn out after they punish a transgressor, changing the punisher to a bystander. Lastly, the bystanders are the most people in society, and the ones who can be the victims of transgressors. When they are transgressed toward, they have a chance to become a transgressor or a punisher.
To effectively model this problem, we first had to make some assumptions. We first assumed that the population remains constant. Accounting for changes in population was too complex to model within our time frame. We assumed that transgressors can only act toward bystanders, as punishers would deter transgressors from acting on them. Next, we assumed that punishment always has a chance to alter a transgressor, giving all transgressors a chance to change their ways. Coinciding with this assumption was the assumption that every transgression has a chance of being punished. We assumed that bystanders would remain bystanders unless acted upon, as there would not be an impetus for their change otherwise. We assumed the same for punishers and transgressors. We also assumed that people are not punished unless they commit a transgression, as without this assumption, the boundaries between transgression and punishment themselves become blurred. Our model renders punishments as instantaneous, because accounting for the time frame associated with various punishments and the status of those population members was not achievable within our time frame. Because our model is compartmentalized, we had to assume that our three groups were distinct and did not overlap in any manner. We then assumed that no population member could go directly between being a transgressor to a punisher or vice versa. This scenario presented itself as highly unlikely and added unneeded complexity to our model. Finally, we determined that each group would have a starting population. With these assumptions, we could move on to developing our model.
Our model is a compartment model, not too dissimilar from an SIR model, where there are three groups of people that individuals move between. We have three equations, each giving the rate of change of one of the groups. The value of these equations depends on the current populations of each of the groups, as well as 6 constants. A is the chance a transgressor will transgress towards a bystander. B is the chance a punisher will punish a transgressor. C and D are the chance that after being transgressed towards, a bystander will become a transgressor or punisher respectively. F is the chance a transgressor will become a bystander after being punished. Lastly, G is the chance a punisher will stop being a punisher after they punish a transgressor. B, T, and P are all proportions of the population rather than exact numbers to make our model more general. When the three equations are added together, the terms all cancel out, meaning that the rate of change of the total population is 0, which is in line with our assumption of a constant population. This table shows the constants values and the starting populations in our initial simulation. These values were based on real-world data where we could find it. For example, the population of transgressors was based on what proportion of people committed a crime in a given year. Some values, unfortunately, are nearly impossible to measure or find data for, so we were forced to infer plausible values.
Once our coefficients were developed, we moved on to evaluating our model over a period of 100 years to analyze the stability of this population. The nature of this evaluation assumes that the behavior of the three groups does not change over time. We used Matrix Laboratories' built-in ordinary differential equation solver to evaluate our system of differential equations. This solver uses a six-stage, fifth-order Runge-Kutta method. On the right is a graph of our three population proportions over time. These populations are fairly stable, exhibiting low total amounts of change. When compared to the starting population of 4% transgressors, the average number of transgressors over the 100-year period was 4.49%, showing a slight increase in the total proportion. Let's compare the percent growth of each proportion. The transgressor population increased by 24.8% and the punisher population by 76.9% over this period. The bystander population decreased by 1.24% as bystanders either became transgressors or punishers. This model shows a general trend toward a more polarized population. After evaluating our model using realistic coefficients, we performed a sensitivity analysis to determine which variables were most important. During this sensitivity analysis, we kept our initial populations the same to observe what effect changes in variables would have on a realistic population. We increased and decreased variables by 25% of previously determined values, and then measured the change in the average transgressor population over 100 years. We took the average of the absolute percent change in average transgressor population between the increase and the decrease of the variable to determine the volatility of that variable. We found that variables A and C had the greatest impact, while variable G had the least effect. The greatest change we observed was a 3.1% change in the average transgressor population due to a 25% change in the value of C.
Remember that C is the chance a bystander will become a transgressor, and it makes sense that affecting the source of transgressors would have the greatest effect. A society trying to be stable and lower the number of transgressors should try to stop the source of transgressors, breaking the cycle. In the real world, lowering C could come in the form of providing greater assistance, such as counseling, to victims to prevent them from becoming transgressors. The other constant with a major effect was A, the chance that a transgressor would transgress against a bystander. This result makes sense. Lowering how often people commit crimes leads to less people being victims and thus less criminals. A society could decrease the value of A by using proactive measures to stop transgressors from transgressing. A real-world example would be preventing access to firearms to stop people from committing gun crimes. The other constants, including how often punishers punished, had much smaller effects. According to our model, punishing every offender is not the best goal because it is not particularly effective at reducing the population of transgressors. This also implies an authoritarian state constantly monitoring and punishing its people will not be much more stable than a freer society, having a similar number of transgressors.
Finally, we must address the strengths and weaknesses of our model. The strengths of our model lie in its attention to the flow of people between groups. We were able to account for punisher burnout, transgressor rehabilitation, and bystander change. Our model is also scalable to any time frame of interest, given the caveat that human behavior does not significantly change during that time. This may become less applicable as technology continues to shape our world. Our model does not base itself on population size and can be used on populations that are large or small. Its use of proportions makes it a great tool for comparison. Our model also allows for different behaviors and scenarios to be evaluated simply by augmenting coefficients within the model to reflect the desired situation. Due to our assumptions in our time frame, our model inevitably has its weaknesses. It does not account for changes in population size due to births, deaths, or the introduction of new people. Our model also lumps all punishers into one group and all transgressors into one group, removing some of the nuance that exists in the real world. Next, we assumed that only specific groups commit transgressions or enact punishments. In reality, these groups are not so distinct. Finally, we do not account for outside circumstances such as financial incentives causing people to take on the punisher or transgressor roles. These are the sources we utilized during the creation of our model. Thank you.